high-quality images at 24 microns, which allow about 20% of the background radiation to be resolved into individual sources. Those individual sources have a redshift distribution which extends to 0.7 at peak and out beyond 1, and so it clearly shows strong evolution of population. At longer wavelengths still, and poorer resolution, ground-based images have resolved approximately 30 to 50% of the background, showing that at higher redshifts, there's still quite a lot of emission coming from far-infrared luminous objects. And we've got more information than just the backgrounds, but it's more difficult to compare the relative intensity if you look at the distribution of fluxes than if you just look at the background level directly. Now, an example of a region which shows the relative strength of emission at different wavelengths is this now 6-year-old image of the cluster Abel 1835, showing the optical members of the cluster and background galaxies, and then highlighting in contours the far-infrared redshifted emission from background objects, magnified by a factor of order of 2 to 3, in this case from redshifts 2.5 and 2.3 for the most powerful sources of emission. And it shows that our current capabilities allow us only to see a very small fraction of the total galaxies present in the far infrared. Now, the energy coming from these galaxies is comparable to the energy from all the optical galaxies in the background of the cluster, but only 2 are very significantly detected. ALMA will revolutionize this and give us a picture in the far infrared, redshifted to the submillimeter, which matches the optical resolution. There's about 25 images of clusters like this. Many of them have got redshifts, and by adding Spitzer information as well, we get a better idea of the spectral energy distribution of these galaxies and find new examples. The problem we have, though, so far is almost every example of a galaxy with a good SCD and a multi-wavelength study are all in the ultra-luminous class. They don't connect with the well-established luminosity function of galaxies from Lyman break surveys and from redshift surveys. They're just separated in flux too much. If we want to go inside galaxies to get information about the astrophysics at the moment, we can do that in an unresolved way. We can get a spectrum of CO rotation lines, so I'll show what the molecular gas is doing in ultraluminous galaxies, admittedly. This paper by Kartik-Sheth et al. Shows a multiple image in Abel 2218, detected in a continuum in the submillimeter shown by the contours, and then with an image from the OVRO interferometer overlay showing individual detections of line emission associated with CO at each of the centers of the 3 multiple images, and then it is overlaid on the HST image. This provides us with an estimate of the mass of these objects, estimate of the mass of the molecular gas inside, which is typically comparable to the stellar mass you estimate from the optical colors, and is associated with objects of 10 to the 11 solar masses, also within a few kiloparsecs. So they're not only luminous objects, they're also massive objects. So we're looking at the top end of the mass function and the luminosity function happening at moderate redshifts here at 2.5. In some cases you can get higher quality spectra. This shows a small galaxy in another cluster field, which is magnified to give a very high quality spectrum from the Plateau de Bure interferometer. And another example of a galaxy not lensed, no, it is lensed this time, Abel 851 good source, which is actually, although a single object in the discovery images at submillimeter wavelengths, is split into 2, each of which has an individual detection at higher resolution from the ERM interferometer and a very clearly defined velocity width, hopefully giving some idea about the dynamical mass of that system. This is also possible to extend to the infrared. As yet, I don't have any information about the nature of these things in an IFU spectrum, but from a long slit spectrograph, you can certainly see velocity structure inside these galaxies. It shows a NIRSpec 2-dimensional spectrum of both H alpha and nitrogen-2, with some extension and some shear in the line running to the middle of this galaxy in the HDF. We've got about 25 of these spectra, and according to whether the optical lines in these galaxies are identified with AGN emission or not, then you can see a relatively strong or weak underlying broad line component in an infrared spectrum. In principle, telling us more information about the power source, whether there's an AGN present, and how much it controls the luminosity of these objects. We've been trying to get some metallicity estimates from oxygen line ratios, which is coming along but is time consuming, and hopefully is something which will become much more easy with adaptive optics over the next few years. So we can also, I think still it's viable to target the brightest examples of integral field units, but only the brightest objects are present, and I think we're going to do much better when different facilities come along, but ALMA particularly. The redshift distribution we found so far for the things that have been identified in both and in the field from a combination of radio surveys and submillimeter imaging led by Scott Chapman, who's just moved out of Caltech to Victoria, is